Okay, so C9 is all about fossil fuels and their combustion. So we're going to start with crude oil. Now, crude oil is a mixture of a very large number of compounds. The large majority of these compounds are hydrocarbons, which are molecules made up of hydrogen and carbon atoms only. So crude oil is basically unrefined fossil fuels, and we need to know about its formation. So millions of years ago, there were many tiny animals and plants in the sea. When they died, they fell to the bottom of the sea, and at the bottom of the sea, they were covered in mud. Over time, layers of rock built up on top, and this rock put the dead organisms in hot, high pressure, low oxygen conditions, and these conditions over millions of years formed crude oil. So that's a little story that you need to learn for explanation questions, maybe 4 or 6 markers. And what this basically means is that we could call crude oil a type of ancient biomass. And we're now moving on to look at hydrocarbons. So again, hydrocarbons are compounds that contain hydrogen and carbon atoms only. We call them organic compounds, and they are mainly used as fuels and to make plastics. Simplest hydrocarbons are called alkanes, and the large majority of hydrocarbons are alkanes. Alkanes are part of what we call a homologous series. That means that they have the same formula, which you need to learn is CnH2n plus 2. That means they differ by CH2 in their molecular formulae. So that is, for example, CH4 when you write out the formula of an element or compound. So they differ by CH2 in their molecular formulae from neighbouring compounds, and they show a gradual variation in their physical properties such as their boiling points, but they have really similar chemical properties. They are all described as saturated hydrocarbons, and that is because they only contain a single carbon-to-carbon covalent bond. For example, ethane. Ethane's molecular formula is C2H6, but you might be asked to draw out the structural formula. C2 tells us that we have 2 carbon atoms, so they will be joined together by 1 covalent bond, and H6 tells us that there are 6 hydrogen atoms. So the structural formula for ethane would look like this. The next topic is fractional distillation, which is essentially how we separate crude oil into parts that can be used, for example, as fuels. So you do need to learn the details for this because it might come up in 4 or 6 markers. The crude oil is heated and evaporates. Now, as the gases move up the fractionating column, they cool down. Each fraction condenses at a different temperature, so it is collected at a different point. Each fraction contains hydrocarbons with a similar number of carbon atoms. The vapours move up the fractionating column, and the further up the column, the cooler it becomes. Bitumen has a very high boiling point, and it doesn't evaporate at all when the crude oil mixture is heated. It is therefore collected at the bottom of the fractionating column. The refinery gases have a very low boiling point, and they do not condense at all. Instead, they pass out the top of the fractionating column. So moving from the bottom of the fractionating column to the top of the fractionating column, down at the bottom we have bitumen. Now its uses include fuel for ships, lubricating oil, and in making road surfaces. Moving further up we have diesel oil, which is fuel for diesel engines, kerosene, which is used as jet fuel. Even further up we have naphtha, which is used in chemical production, and nearing the top now we have petrol, used in cars, and then right at the top is the refinery gases, which is used as fuels. As you go up the fractionating column, volatility increases. Volatility is the ability of something to evaporate. Now, we've already spoken about the refinery gases having really low boiling points, so they don't condense at all. They stay in gaseous state. Also, flammability increases as you go up the fractionating column, and something that is flammable is easily ignited and capable of burning rapidly. However, viscosity decreases. Now, viscosity is the resistance of a liquid to flowing or pouring. So it's essentially a liquid's thickness. And finally, chain length decreases as you go up the fractionating column. And when I'm talking about chain length, if you picture structural formulas, ethane is a much smaller molecule than octane. If we just look at the molecular formula there, you've got C2H6 versus C8H18. And we have a few more definitions to learn. So first of all, what is distillation? Well, distillation is just the separation of a liquid from a mixture by evaporation followed by condensation. A fraction contains hydrocarbons with similar boiling points separated from crude oil. They've also got a similar number of carbon atoms. For example, methane and ethane are likely to be in the same fraction because CH4, C2H6, one carbon atom versus two carbon atoms, similar numbers of carbon atoms, so they're really likely to be in the same fraction. Two quick notes here then: the smaller the molecule, generally the lower its boiling point, and fractions are collected and processed. What is combustion? Well, it is simply the burning of hydrocarbons. When fuels are burnt in plenty of air, they transfer lots of energy to the surroundings. And we have our little fire triangle here. How do we make fire? Well, we need oxygen, fuel and heat. What makes a good fuel? A good fuel burns easily, it is readily available, and it doesn't produce a solid residue. Now, there are two types of combustion. The first one is complete combustion. Now, complete combustion occurs in plenty of oxygen when we burn with a clean flame. No soot or carbon is formed, and the products of complete combustion are carbon dioxide and water. For example, CH4 plus 2O2 makes CO2 plus 2H2O. We've got carbon dioxide and we've got water forming, so we know it's complete combustion. For example, again, we've got C4H10 plus 6.5O2 makes 4CO2 plus 5H2O. We've got CO2, we've got H2O. This is complete combustion. And then we have incomplete combustion. Now, this occurs when there is not enough oxygen. We burn with a smoky flame, soot can be formed, and carbon monoxide is formed. This is a colourless, poisonous gas. So the products of incomplete combustion are CO, carbon monoxide, and water. For example, C3H8 plus 3.5O2 makes 3CO plus 4H2O. We've got carbon monoxide and water here, so that's incomplete combustion. Now, to test for the products of combustion, to test for the presence of carbon dioxide, we bubble the gas through lime water. If carbon dioxide is present, that lime water will turn cloudy. To prove we've made water, we would use anhydrous copper sulfate powder. It starts off as this white powder, but it will go blue in the presence of water. Alternatively, we could use cobalt chloride paper, and this will turn from blue to pink in the presence of water. We now have a mini focus on carbon monoxide. So carbon monoxide is a poisonous gas that binds to hemoglobin in your red blood cells, reducing their oxygen carrying capabilities. It's colourless and odourless. However, it can be detected by electronic detectors fitted near boilers, and its symbol is CO. Cracking. Cracking is a reaction where larger saturated hydrocarbons are broken down into smaller, more useful hydrocarbon molecules, some of which are unsaturated. So our original starting hydrocarbons are alkanes, but the products of cracking involve alkanes as well as alkenes. Alkenes are members of a different homologous series. We need cracking because there is not enough demand for some of the heavier, larger hydrocarbons. They are liquids or solids and they don't burn easily. That makes them poor fuels. Moreover, smaller chain hydrocarbons are more useful for fuels, chemical feedstock, as well as making polymers. So large hydrocarbons are cracked into smaller ones by either thermal cracking or catalytic cracking. Thermal cracking involves really high temperatures, usually around 900 degrees C, and high pressure. It's then mixed with steam. Catalytic cracking is used more in industry, and this is where we involve slightly lower temperatures and pass the compounds over a zeolite catalyst. Both of these types are forms of thermal decomposition, where we break a larger molecule down into a smaller molecule. We're now going to zoom in and look at alkenes. So alkenes contain a double bond, for example, the likes of ethene, propene. Methane, however, does not exist because it only has one carbon atom, so we can't have a double bond because it can't be bonded to another carbon atom. So we call alkenes unsaturated hydrocarbons, and this is because they are not bonded to the maximum number of other atoms. Alkenes' general formula is CnH2n, and alkenes burn in air, but not as well as alkanes. A positive test for an unsaturated hydrocarbon is that it turns orange bromine water colourless. Orange bromine water does not react with alkanes. You could be asked in the exam to crack a molecule. So for example, if I'm asked to crack C12H26, I know that I need to end up with at least one alkane and at least one alkene. So I pick a number, so I'm going to go with C6. Now I'm going to start by making my alkane. So the formula for an alkane is CnH2n plus 2. So C6, 2 times 6 is 12, plus 2 is 14, so I'd end up with C6H14. Now I've already used up 6 carbon atoms. 12 take 6 is another 6, so I need another C6, but this time I need to be making an alkene, and the alkene formula is CnH2n, so 2 times 6 is 12. C6H12, does it work? H14 plus H12 makes H26, so yes, I've made C12H26. Then again, if I was asked to crack C14H30, I might make ethene first, C2H4. I could then make heptane, C7H16, and then I could also add pentene in there, C5H10. There are loads of different ways you can do this, by the way. And the last thing really is to learn the names of the molecules, but I quickly want to point out that the number after the C refers to how many carbon atoms you have, not how many bonds. Okay, so we've got CH4 is methane, C2H6 ethane, C3H8 propane, C4H10 butane, C5H12 pentane, C6H14 hexane, C7H16 heptane, and C8H18 octane. And that's all for today, so see you next time.